So, hi everyone, and welcome back to the CSMR Soft Matter Seminar Series. My name is David Greer, and I'm the Director of the Center for Soft Matter Research at NYU. I'm super happy today to be able to welcome our speaker, Heinrich Jaeger, from the Department of Physics and the James Franck Institute at the University of Chicago. So Heinrich and I are old friends. Heinrich, let's see, how far back in time will I go? Got his start. He got his PhD from the University of Minnesota, working with Alan Goldman on granular superconductors. So the granular theme you might think it's sort of creeping in right from the get-go, but it's not really so. The idea was there that the disorder was having interesting influences very interesting influences on the superconductivity. And so to follow that up, I guess Heinrich went off to Delft next, to the Netherlands, to work on nanofabrication, some of the earliest work on quantum devices based on quantum confinement, which created by microfabrication, which was really, really exciting stuff again. And so then he moved from his postdoc to a faculty position at the University of Chicago, where he's been since. He's served as director of Chicago's MERSEC, as director of the James Franck Institute, and he is one of the world's great experts, in fact, one of the founding experts of the field of granular physics, the physics of granular matter, not just in the aspect of the statics of jammed matter, which again is a huge theme in soft matter, where Heinrich did some of the seminal work in how forces redistribute themselves in random packs, but also in driven granular matter, where you have granular convection, all sorts of interesting dynamical states, including beautiful high-speed video images of what happens when granular matter is really interrogated very, very rapidly by large forces. I think what he's going to be telling us today is about, in some sense, taking that driven theme to an extreme, where you're driving the system so hard that in fact it levitates, it floats, and becomes a new state of matter, acoustically levitated granular matter. And so with that, I'm going to turn it over to Heinrich to have him enlighten us with sound.
All right. Well, thank you, David. Thanks for inviting me. Thank you for this really nice introduction. Thank you all for being here. I want to tell you about work we've done at the James Franck Institute over the last couple of years, driven primarily by graduate student Melody Lim, and now postdoc Brian Van Zaders with graduate student Tali Kine and Brady Wu, and undergraduate Annie Xia. And then there will also be appearance of some prior work on levitation of prior graduate students, Victor Lee and Adam Klein. And we've had wonderful collaborations with theory colleagues, Anton Suslov, who's now University of Bath, and also my colleague Vincenzo Vitelli. So the question is, what is levitated granular matter? So let me give you an idea of one example here that I will talk more about, but just to set the stage, you're looking from the side, there's a surface with small particles. They're about 100 to 200 micron in diameter. There's an intense sound field generated coming from above that reflects off that surface, forms a standing wave. And it is so strong, the sound field, that it actually pulls off particles from that surface, drives them into a levitation plane. And in that plane, these particles start to interact. Right? So they form this, for example, this beautiful raft that turns around in front of you there. So one of the issues you see right away is this is a complex situation, lots of interesting dynamics. It is clearly driven, and also it is in a underdamped regime. So that's something that is particularly nice here for this type of experiment. We're getting into a regime that often is hard to get to when you look at small particle assemblies. And of course, we use high-speed video to look at this and track individual particles. But before going into more detail, let's take a step back, talk about a little bit the history. So you all are familiar with these beautiful Chladni figures. You put dust on a vibrating plate. The particles, they show you the mode structure. Well, those are transverse waves that are visualized that way. So the first person who visualized longitudinal waves was this gentleman here. Let me get my cursor going. August Kundt. This is paper from 1866, and he had a long tube. You see a sketch there, and filled with gas, and then excited by a sound wave from one side. Particles, fine dust particles, they would momentarily levitate and then organize themselves in patterns, as you see here, that corresponded to the nodal positions of the pressure nodes, right? And he used that actually to look at the speed of sound in various gases. So now imagine you take that tube and instead of having it horizontal, you need to turn it vertical, right? And then you have horizontal planes for the pressure nodes. And I'm showing that here in a little bit modern setup. This is a piezoelectric transducer, and a reflector above it is just a little glass, hourglass, and you can put particles in there, right? Particles that then are in these standing sound field nodes. Now, that 20 years ago, that was kind of the state of the art. That's how you generated acoustic levitation situations. But nowadays, you can go much further. So I'm showing you on the very left here a sketch from a really interesting and good review by Andrade and co-workers, where they go through the current state of the art, at least from 2020. And often you don't just have that single axis, so-called Langevin horn, but now you can make whole arrays of acoustic transducers. And what that allows you, for example, is also to look at the phase relations of the drive and get into very interesting dynamics. You can even make vortex tractor beams with that. You don't necessarily even need a reflecting surface. You can use a big object as the reflector itself. Here in the middle is a beautiful example of, a little 3D printed structure you buy for a few bucks each. These rangefinder transmitters, you place them in these particular patterns and make yourself a so-called tiny lev, first coming out of the Drinkwater group, and you can levitate things over quite some distances. In fact, if you steer the phase relationship and the amplitude relationship with these transducers, you can levitate large objects without any reflector. You see that here, this is a 30-millimeter sphere, approaching the wavelength of the sound here, or you can even move them around over an array like that. So these are arrays that by now have up to 1,000 or so elements. Now, I will not talk about those arrays today. I will, in fact, talk about the simplest possible one is, again, just this Langevin horn. That's what it is. And here in this sketch, it's a transducer that sends out sound waves that bounce off some reflector, right? In our case, could be a piece of plexiglass. And we drive this usually with a high frequency, so 40, 45 kilohertz, piezo driver here. And then the resonance condition is that this gap distance h has to be a multiple of half a wavelength, right? And so the air gas pressure in this situation is a sinusoidal function of the position. And I measure here for this talk today, everything off the nodal plane, right? So this is z equals 0, it's right here. And the gas pressure has this particular functional form for such a standing wave. And the gas velocity, the air velocity, is just simply the derivative of this, and it goes with the cosine, right? And then, as you already saw with these styrofoam balls, the particles will levitate in the pressure node right there. And for us, for the following, the typical particle diameters will be, a fraction of a millimeter for most of what I show, but they can also be larger. In fact, they could be up to maybe a couple of millimeters, just to set up the experimental conditions. And you might imagine, right? I mean, having gone to music events or so, where you can feel the music. If you want to feel it to the point that it levitates you or a particle, you have to put dramatic sound levels in there. And that's why we go to ultrasound, so we can still hear ourselves, right? So these are levels typically in the 160 decibels range or so. So the energy density is quite high in there. Now, in that range, that the particle diameter, or here A is the radius, is much less than the sound wavelength. I told you our wavelength is of the order of 7 millimeters. Our particles are a fraction of a millimeter typically. You can make a scattering expansion of the sound field, right? And you can figure out the forces that such a point particle experiences due to scattering sound waves. Remember, it's a standing wave in there that runs up and down, and it will also hit the particle, right? And create a potential U here, which was first calculated by Gorkov in the early 60s. We call it the acoustic potential, Gorkov potential, right? This U, and then the force is simply the gradient thereof. So it depends on the particle volume here. It depends on then the RMS expectation values of both the pressure and the velocity. And there are these prefactors, the density of the air or gas, or the surrounding medium, and the compressibility. And obviously, you know, those two are related then via the wave speed. And then there are these interesting prefactors F1 and F2. They come from these scattering expansions. And they go back, you see that down here, to ratios of compressibility. So P is the particle and 0 is the surrounding medium, and also the density ratios, right? And now if you look at our experiments, we're living in a situation where there's gas and the particles are solids. So essentially both of these factors, F1 and F2, they turn into, you know, unity, essentially, to pretty good approximation, right? And so that means then that in fact, if you look at this expression, you can think of this term here as the kinetic energy and this as the potential energy. This thing is minimal, so that's where the particle would want to go when this pressure term here vanishes. So the particle would go into a pressure node, right? So in the pressure node, that's where also then this velocity is maximum. On the other hand, and this is studied also a lot, you can have a situation where these sound waves are generated, let's say, in water. So the medium is a liquid, and then you have little bubbles in there. So now the P corresponds to an air particle. So that means then this ratio now is bigger than 1. This F1 flips sign, and suddenly an air bubble will move to an anti-pressure node, right? So just to set us up here. So for us, the particles are in the pressure nodes. Okay. Now, if you look at this for the specific case of a simple standing wave, as I had in our experiments, you can figure out the force or the potential, and it turns out to be the sinusoidal function here, twice the wave vector times z. You know, it's essentially a spring right around the nodal plane. Okay, remember, I put the z at 0, right? That's the nodal plane. And that means if I now put the particle there, it sits essentially like a simple harmonic oscillator in a beautiful confined z potential, right? Now, there is some damping because of the air. Damping with air is actually small, but it's good to take into account. So you see an example of a particle we perturbed, right? And then you beautiful exponential fit there. You pull out these parameters and you plug them into your equations there and predict the behavior. Well, the particle will obviously oscillate then, right? And what's its oscillation frequency? Well, the spring constant, the effective spring constant, so that's from here, right? This K depends on the volume that the particle displaces, right? So it depends on the particle volume. The particle mass depends on that. So K over M, that spring constant, really depends only on the density of the particle in that surrounding fluid, which is air. So it's really like a buoy in air, right? It's an air buoy. All right, so that's for the vertical displacement. And so let me give you one example where early on in our lab, we used this setup. And we use it, in fact, for precision tracking of collisional charging. So we put a particle right here in this gap between a transducer and a reflector. Transducer is a metal horn. The reflector we metallized, so you can put actually electric fields over there, put little particles in there. And now, let me just make sure I get my cursor changed again here. This is, I should put on, this is work by former graduate student Victor Lee. So now we have the particle sitting there in that node, and you see here the red circle. And I show you the Gorkov acoustic potential for that case. In fact, we put a little notch here to make sure it's also laterally confined. Okay, and then we used this potential to keep the particle afloat, but we could also turn just the sound field off, in which case the particle would simply collide with the plate. And on the rebound, we just pick it up by turning the sound field back on. So you see here is, in our case, typically about 10 milliseconds. So you do that under computer control, right? So what you can do with this is you can trigger single collisions at will, all right? Why would anybody be interested in single collisions of granular particles? Well, there is a lot of interest in figuring out the charge state of granular matter here on Earth, dust devils, and volcanic ash clouds. You see that there's so much charge in it, you even get lightning inside the dust cloud. But also, and that is something that tickled us for a long time, and I don't have time to get into the details, the very earliest stages of planet formation. I mean, we're starting from micron-sized particles, involve collisions of particles. And we believe that actually charging is important. And it turns out that in contrast to magnetics, for charge, there's still dielectric insulating particles. There are just massive questions out there that are not fully answered yet. You know, how does net charge build up by collisions, let's say in these clouds, from initially neutral dielectric particles? What actually transfers charge if it builds up, right? And how much charge is transferred in each collision? So the last 2 points is something I want to talk about today with you just a little bit to show you how ultrasonic levitation can really bring in a new level of precision there. So here we are again. And so we pick up the particle, all right? And now we could put an electric field on and just move it around if it's charged and measure, for example, how much charge it has, right? It turns out that we have resolution issues with the camera. We want to amplify that. And one way to do that is to sweep the electric field we put on there and drive this particle into resonance. Remember, it was a little oscillator, right? With a certain resonant frequency. Turns out it's of the order of 50 to 100 hertz. So we do that, well, Victor did that. And here you are, we sweep the frequencies to a range, let's say over time here, maybe between 60 to 100 hertz, all right? And then you see the amplitude at some point that we measure as a peak because we drive it through resonance. All right, so that's the idea. We sweep the frequency. As we do that, this thing goes to resonance. Now look at the equation I showed you before. Should look familiar, right? That's basically F equals MA. This is MA, there's the air drag. This is the acoustic force. I put it in now in its full glory there with the sign. There's gravity, of course. And this is now the swept force due to the swept field. So it's Q times E, the electric field, is the voltage applied over the gap distance, right? And I do that with an AC field, and I let the AC field go from some initial frequency at some rate up. That's what this red line showed you a minute ago. So it's a complicated equation, not so easily solved. So what we're going to do is now we measure experimentally these max amplitudes and also the oscillation frequency, the resonance frequency at that maximum, right? And we solve these equations numerically in some sort of iterative fashion, compare with the experiment, and finally fit it to extract what we're really interested in, which is this charge Q right here. All right. So that can actually be done in this iterative fashion. And the interesting thing is that we get a charge resolution out that is truly remarkable, right? I mean, there's nothing you can measure better than resonance frequencies if you want. We're essentially just limited eventually by measuring this max amplitude. The pixel size of the camera really limits everything. And we turn out to be 1,000 times more precise than you could get with a Faraday cup. Well, for a Faraday cup, you'd have to kind of get that cup in there also, or maybe touch the particle or be really clever. This works without any touching, totally under computer control. So here's what Victor finds. So he takes, for example, a polyethylene particle and drops it, in this case, about 1,000 times under computer control. You notice, by the way, this happened to start out a little bit positively charged, and then we go eventually and charge it more and more negative. But look at what's so remarkable here. For those of you who have ever tried to measure charge on particles, over 1,000 collisions with one single particle, right? we get a slope that is, I mean, you don't have to believe that precision, but it is down to a few electrons per collision on average, right? So that is remarkable precision. You might wonder why this doesn't saturate, and that is because these particles also spin, right? And so we're probing different spots on the surface every time we come down. We actually know the impact velocity. We measure that too, and we can kind of figure out the deformation of the particle. We know how much is transferred per area also that way, roughly. Now, if you don't do any collisions, you know, you might have thought, well, maybe some of this charge is just leaking away, at least over 24 hours or so it doesn't. There's some experiments, by the way, at Emory University, just in Burton now, where they go much longer, and eventually some charge will leak off. So, but over these time scales that we're talking about, they don't. And now here, in this case, we had a particle collide with a plate, right? With polyethylene particle, aluminum bottom plate. And you know, you transfer more and more negative charge to the particle. Well, that makes sense because of where aluminum and polyethylene are within the triboelectric series, right? So this was kind of a test experiment. But what we really want, of course, is imagine particles that come together and collide, and they are the same material, right? And the triboelectric series would tell you if you collide same with same, there shouldn't be any charge transfer, right? And it turns out, so Victor does that now, makes a glass particle, coats it with indium tin oxide to still put electric field across from the bottom, and now modifies the glass particle or the glass surface by suitable salinization treatment. So you can have hydrophobic, hydrophilic collisions, or just hydrophobic on hydrophobic or hydrophilic on hydrophilic. And you see now it depends very much on what kind of surfaces come into contact with each other, right? And so what that leads to, and you can ask me later, I'm happy to give you more detail, that in fact, what we believe now happens in these cases of dielectric particles, that the charge transfer is actually done by OH minus ions, so that the water dissociates, all right? So it's not electrons, OH minus ions. And the really interesting thing then is that the sort of a triboelectric series, we should really think about a wettability series, right? And it is actually only recently that people put water at the top of the triboelectric series, is a reference for that. So really what I think most of this triboelectric charging is actually just transfer of OH minus ions. All right. So that was now nice. It actually really took us a while to get there, but it's of course charging with a plate. What you really want is particle-particle charging. And so now you need to confine the particle in the plane, in the levitation plane. In fact, you want to confine two particles. So you see here, we got two of these blue regions where now particles confined. We now put a little channel in the bottom to change the boundary conditions such that we get essentially one-dimensional confinement also along the x direction here, and confine it in y. And then turns out if you change the boundary conditions by moving a piece of plastic in and out of this two potential well situation, you can turn it into a single potential well. So two particles start out here, they're happy in their potential wells. You pull the so-called finger out, and you see here, this is a space-time diagram, so the white ones are the particles that sit out here. You pull this thing out over time, they're going down, they come together, they collide, and then they come back out, right? And once they're back out in their wells, we turn on the AC electric field and measure the charge. Bam, measure charge over and over again, right? And so you can do this, what Victor did. This is Adam Klein's work here. Same material on same material, depends a little bit on exactly what the surfaces are, but the amount of electrons transferred is really small, 10 to the 4. Now you change it by sulfonating, let's say one of them, you really build up charge, right? So it's really the surfaces of these particles that play a key role here. And you couldn't have done these measurements in any other way that I know of. So ultrasonic levitation really helps to isolate particles and give you access to it and control what they do.
Excuse
All
me,
right.
Heinrich,
Yeah.
could you explain again why one particle picks up one sign of charge and the other particle picks up the other? Did you explain that?
Yeah, so basically what happens is that on the particles, there is a distribution of little wet patches where the molecularly thin layers of water exist. They're dry and wet patches. And so as these things collide, they basically transfer OH minus ions from a wet patch to dry patch. Now, you shouldn't think of this as, you know, a thick droplet of liquid. You should think of this as a molecularly thin layer. And people have recently studied even on mica with some techniques where you would expect a molecularly thin layer beautifully covering all of mica, right? Atomically flat. The water breaks up in little patches even there, right? So that you should think of patches.
Heinrich, can you do water on water?
We probably could. Water drop, we have not done that. In fact, that would be a great experiment to do. Yeah. Yeah, so
that's the way lightning works, no?
Yeah, maybe, sure. We could try that. We have not done that. Absolutely right. So these are brand new things. You see, this just came out last year. So there's much more to do.
But can I ask, along the same lines, if you have every particle has some places which are covered with this water and some places which are dry. And if two particles collide, then you have a random choice. Which particle receives positive charge and which receives negative charge.
That's correct.
And then each particle goes through sort of random walk of charge. It sometimes goes upward, sometimes downward. So it should grow as square root rather than as time.
No, so good. You're absolutely right. And this is maybe something I would love to tell you in much more detail about. So it turns out you're absolutely right. It's a random walk. Then something needs to break the symmetry. And the symmetry is particle size. So to the extent that these particles are not totally identical in size, or to the extent that they have different surfaces, right? Like polystyrene, sulfonated polystyrene, they will actually charge. So that's why polyethylene versus polyethylene on the left here, equal size particles, they start out with some charge distribution on each size. They're not gonna do much, right? But if you have a size difference, that would break that symmetry, and be happy to tell you more about it maybe afterwards. Good point.
Thank you.
But now let's add another particle. Let's go from a single particle on up. So here's the Gorkov potential, the acoustic potential term again, and I got rid of these F factors because they're essentially one in our case, right? And this is the empty cavity here. This is what a point particle would experience. You see where it's blue, that's where it would like to be. I put in Melody here, who calculated that finite element, put in one more thing in the horizontal direction. These are boundary conditions that correspond to our situation, meaning the cavity is actually open, right? So there's a transducer bottom and top rather, and reflector at the bottom, and the side walls are open here. And that means you get also a little bit of confinement automatically in this X direction, okay? That's just a matter of the boundary conditions. And you got this sinusoidal dependence in the Z direction that I showed you already. Now, if you put a second particle in there and you're still in this Rayleigh limit, then the potential experience by that second particle due to a first one sitting right in that nodal plane in the X equals 0 position on the axis, that potential is shown here in the second plot. All right, and that is the force that second particle experiences because waves scatter off the first particle, right? And that force now is called a secondary acoustic force. It's due to scattering from one onto the second and back and forth, all right? And we'll exploit that in the following, if we go to more than one particle. And so here's a little bit more about that. So you can extend that in that Rayleigh limit to multiple particles as long as they are point scatterers. So this is very important work by Silva and Bruce from 2014, where you look at a source particle here that scatters sound off to some other bunch of particles around it. And then the force on the particle is really both the primary force from the primary beam, you know, the initial standing wave, and then whatever comes from the scattering of the other particles, call that the interaction component right here. And if we're in the nodal plane, already, then you can think of this again being decomposed into two things. One is a radial direction, and one would be one that kind of drives you, if you're a little bit out of the radial plane, into the radial plane. And I show you these two components right here. This is the calculations based on Silver and Bruce that Melody did. You know, this is the attractive force. If two particles are separated by some distance r, there's this very short range force, goes like 1 over r to the 4th power. And E0 here is the energy density just from the sound in the cavity. We can control that by turning the overall amplitude of our piezo elements up and down. You see it's a rather short range. And then if the particle, the second particle is now a little bit out of plane, there's a torque that tries to get it back, or force I should say, rather get it back into the plane, right? And so that's this one right here. So sitting directly above it is actually unstable, right? It would like to not sit there, it wants to be in the plane next to the first particle. And then what Silver and Bruce do, they extend that mean field to then pairwise interactions over all sorts of scatterers, right? So that's the current state of the art as far as I can tell. So now what Melody Lim did to begin with, she said, okay, let's build up a situation where one more, 2, 3, 4, 5 particles in the nodal plane. Now, if you put 1 in, that's 1. You put 2 in, all they can do is they form a dimer. If you put 3 in the ground state, or most compact state is a triangle. You put 4 in, there's only one way to do that is most compact. It's this one. 5, whatever you do, the most compact state is that. However, once you put 6 in, you get degeneracies. Aha, here we are. This is the 5 again. Now here's 6. You can form a parallelogram. You can put them in, so you form what's called a chevron, and you can form them so it forms a triangle, right? So these are all essentially degenerate ground states. And if you go to 7, then you get these other ones. The names are wonderful, right? They are not ours. They're actually from the colloid field. It's from Vinny's group, I think, originally in Harvard, where he calls them flower, or they call them turtle, tree, boat, right? The fun thing here is that once these things come together, right, you got the short range force due to secondary scattering, right? Goes like r to the 4th here. These forces act like bonds. So they pull them together, and now they stick together due to this acoustic force, right? And you have a little chemistry set essentially in the plane, where you make these molecules if you want. In fact, we can do a little bit more. We got an extra knob. Let's suppose I don't drive this thing at the resonance frequency. Let's suppose I detune it a little bit. And by little bit, we mean parts per mil. All right, so you see that here. That is actually generating active fluctuations. So if you look down onto this, or you look up through a transparent bottom, that's just what's done here with a high-speed video, you see that these things, they move around, they rotate a little bit, but also, and let me show you the next one here at the bottom, they wiggle, right? They break apart, and then they reform. Now remember, there's a lateral potential well due to the boundary, so it's a very shallow well. It brings particles back once they get kicked off. And you see that we're varying this detuning here by a factor 10, and so the characteristics are rather different, right? And again, this is in the underdamped regime. This is kind of cool. You get to something that is really hard to get to in the colloidal business. Let me just show you that this is similar to an effective temperature. But first, let's talk about where these might come from. So look, if I just stick a particle into a cavity with a mode in it, there will be a perturbation. And it turns out that the mode structure is slightly changed. In fact, here is the expression for how that mode structure, or in fact, how the frequency will change if you put a particle on axis, right? The particle has volume Vp, the cavity has some volume. If you put it right on axis, it's always a negative depression, it's really strong. And if you put it off axis, there's a z-dependent change of the modes, right? And then the question is, what happens when the particles now also start to move? Well, now the thing is that the modes can't follow immediately, right? There's a lag. And that lag gives rise to a velocity-dependent force. That's really interesting. And it turns out And let's look first on the right here, that the original equation that I showed you for something on the axis, right, with the damping here, spring constant there, gets changed. There's a new damping term. Essentially, it's a velocity-dependent force that comes from this lag of the modes. And it turns out that if you detune such that you are below the resonance frequency, well, then this R star is negative. So this just adds to the viscosity. Now, if you tune a little bit above the resonant frequency, so delta F over F0 is larger than 0, then this prefactor is actually bigger than 0. Here's a minus sign. You see it reduces the effective viscosity. In fact, you turn this into, well, not a superconductor, but you can turn it into a situation where it goes to 0. And in fact, you can turn it negative, meaning it becomes unstable, right? And so then the tiniest fluctuations can start this thing to oscillate. This was work by Rudnick and Barmatz that very, very nicely calculated that. And let me just show you one plot from their paper here. This is the threshold amplitude. So one of these curves, let's say this one here, says if you want to know how much accidental fluctuation you need in order to drive an instability, you see that here, as you don't detune, you have to really perturb it. But the moment you detune it ever so slightly, you just have to go maybe by a few microns, right? So in air. And what's plotted on the horizontal scale is really the detuning, but in their case, they multiply by the Q factor. So Q for our cavities is typically about 100, right? So you see if this is 0.1 or 0.2, we're detuning by per mil amounts, right? If you divide by 100. So this says if Melody detunes ever so slightly, she gets these oscillations going, can drive this thing unstable in the vertical direction. Let me just show you. Again, this is from above, and here we're showing from the side. You can make this thing actually crash on the bottom, and it breaks the cluster up. And in this particular case, then it turns out that the fluctuations are such that particles will move out to the side, come back eventually, and dock somewhere else, right? Form a new shape. And if we change the detuning, we change actually the quality of the, we change the, let me bring that back here. The quality of the fluctuations, and instead of less frequent, rare collisions, you get more frequent, but less intense collisions. So particles effectively explore the perimeter here, kind of hinge-like motions, all right? So what that means is that we can look at the probability then of changing states. And you see that probability here is going nicely exponential with this one parameter we exploit here, this delta F over F. So this is on a log scale probability of changing from one state to the next. And then if you want to ask what's the probability to be in a particular state, well, we got these different ground states here. We can have triangle, chevron, or turtle. And you see how they beautifully can be tuned with this parameter, right? So does that make any sense, for example, that these things come to this particular point right here, so about 0.4, right, or 0.2? Well, let's look at that. So it turns out that if the probability of ducking anywhere here is the same, no preference, if they're all equally likely, and there are 5 spots where this thing could duck, if you start with 5 and now you put the 6th particle there, right? Then each of them is 1/5. And you get these situations where the parallelogram has 2 of these 1/5 possibilities, chevron also, so they sit up here, 0.4, and the triangle is a little less likely. There's only one possibility if it docks right here, right? This is in fact the same thing Manoharan group found for colloids, right? And others probably too. So this is what you would get in a thermal situation. We call it ergodic. But now there's another possibility when particles move really far away, and meanwhile this cluster maybe turns a little bit, they come on some arc trajectory and they come back, then where they dock and what the likelihood is of docking at a particular spot depends on really these angles, right? So you dock in this spot if you're within about a 90-degree sector. If you want to dock at the tip, you only have about a 60-degree angle chance of coming back in that plane. And so you go through, so 90 plus 90 gives you 180 for the parallelogram, and so on. So you add up to, in fact, these probabilities here, 50% here, triangle again, but it's only 60, so 1/6, so it sits down here. Right, so this is what's called the sticky non-ergodic limit. And there's some work by others Wang and company, who found the same thing. But the nice thing here is Melody can actually tune in between very continuously and get to the whole range of situations, both in equilibrium and out of equilibrium. So that was for 6 particles. You can go and add one more, go eventually to turtles if you want. So the same mechanism can be exploited there. And we brought in our theory colleagues, Anton Suslov and Vincenzo Vitelli. At that point, Anton was a postdoc with Vincenzo. Now the 7-particle cluster, it can break apart and then turn into a 6. The 6 can break apart, turn into a 5, and then rebuild. For the 6, there are 2 ways it can rebuild, like I showed you, ergodic, non-ergodic. That gives rise to some interesting probabilities for then how the 7 emerges out of these intermediate states. Put that all together in a Markov chain model, and you come up with these particular probabilities. So it turns out at 7, and presumably also higher orders, this detuning doesn't do that much. The changes are rather slight. But the interesting thing is, that was chemistry, right? You would always like to get at the intermediate states, and we can do that. We see them, we have access to them. And here they are, right? So this is now the intermediate 6 cluster right here. And you see it's different what I showed you before, right? But that's because you have the 7 that can contribute to the 6, as well as the 5 that can contribute, depending on whether particles added or taken away. So we can get to all of these statistics and exploit some beautiful non-equilibrium physics with that. All right, these were spheres. What about particles that are non-spherical? And in the early days, we thought, maybe also led by ideas from colloids and what you guys do at NYU, said, okay, so maybe this is essentially similar to, well, whatever, Casimir force, depletion force. I mean, we want to exclude modes from scattering inside a particle cluster. But then if we bring 2 colloids together that have sidewalls like cubes, right, they should probably stick like this. Well, and then Melody, together with an undergraduate, Annie Jia, did the actual experiments, right? And so here we go. And what a surprise. So cubes stick on the edges. And here's another one, a beautiful, let's see, another movie. Let me see if I can get that up. Look at that. It could do all sorts of things, but it just doesn't want to do anything but get together along the edge. Right, and then of course in that potential it'll oscillate and it'll do this chicken wing thing. All right, so where's that coming from? Well, there are different contributions, right? I showed you already that any particle that's not in the levitation plane wants to get in the levitation plane. So they don't want to connect anywhere else but in the levitation plane. That's good. Then it turns out that if you look at the acoustic potential and you do finite element simulations, that actually at sharp corners, the scattering is enhanced and therefore the attraction due to secondary scattering is enhanced. And you kind of get that also if you make the analogy between, a potential flow, so acoustics and electrostatics, right? So I told you that the velocity was the gradient of the pressure here. So more generally, you can define a velocity potential, which is again the pressure, and then the gradient thereof, which is the velocity here. And so you find that is particularly pronounced right at these corners, right? So a large curvature, that's where this is very blue. That means that's where it's very attractive. And then once such a set of cubes has formed, let's say, and if it ever is not in the plane, so now it's an extended object, right? Maybe elliptical, maybe in the cube case, rod-like. Then there's the primary force that will always drive anything that's flat towards back so that its long axis is within the levitation plane. Right? So this is to dock it at the edges. This is down here to drive it back into the plane. And it turns out that simple scattering theory, a la Silvan Bruce does not capture all of this. This is not simply addition of point scatterers. And so we went to a more involved method. So this is a postdoc Brian Van Zeters, who joined the group and then went and did Lattice-Boltzmann simulations where you could get the fluid particle interaction. And now here are two cubes, right, that get drawn to each other by the scattering and now specifically get drawn in such a way that their corners line up. And not only that, you can then go in and set these things at various opening angles, and you find that indeed you get what we also see experimentally, you know, that there's a torque that drives these particles in these configurations that we observe. And that torque depends on the opening angle, all right? Now, let me just show you some more nice video. So what happens if you have more than two cubes, right? So they form then a longish object, but that's not the only stable configuration, right? As long as they want to be at the edges, you see in a while. And here we put these oscillations on. We put the active fluctuations on. We let this thing move up and down, give it some energy. And so it moves around and finds another spot, right? And here's another one. This is now 4 of these cubes. So it gets more and more difficult for these poor cubes to find the right edge configuration in a ground state fashion, right? Because eventually that various details frustrate this ability to move around and dock at just the perfect position. Okay, and you see, by the way, on the right, these are 3D printed cubes. It's a little fuzzy, right? That's from the 3D printing. They are now millimeter size. And on the left, also, they're large now. Okay, but let's go back to the many particle situation that I started from with you, right? So this is the movie I showed you at the beginning. You know, cubes will also form rafts, but like I said, the edge thing complicates things. So let's go back to the spheres. So here we are. That's the movie I showed you. And you notice that there's some turning, right? Well, so there's not just levitation. There's not just oscillation up and down. There's also some rotation. Let me just show you from below even more what happens. So here we can, in fact, get this thing to spin up. So there seems to be at least moments or stretches of time where in these experiments, there's a more or less constant torque. And you know, we can measure all of these rotation rates and all that. That gets this thing spun up to a point where it deforms and then breaks up. And the nice thing here is, look, and then it comes right back. Remember, there's confinement in the plane. These rafts drift together and they join, just essentially like a liquid, except this is not a liquid. This is a soft solid, right? But look, it's almost circular. So it has something like a surface tension in there, right? So what is this and where does that come from? Now, what are the sources for torque? The Gorkov acoustic potential doesn't give you that. It is essentially concerning conservative forces. But if there is also a phase gradient in the drive, you can set up more complex force landscapes. In fact, those that have non-conservative forces in it. Beautiful new direction there is that of acoustokinetics, and David and Mohammed have a lovely paper out from last year that shows exactly how you can, in fact, control that and manipulate that and use that then to drive particles around. Now, in addition with torques, right? So a little bit of what used to be done or is done with light now moves over into the acoustic field, you know? And of course, like I showed you earlier, if you have transducer arrays, you can control that, right? By changing phase offsets. You can also, and this is stuff Brian did, Brian Van Zeters, our postdoc, you can modulate the boundary conditions ever so slightly. So for example, here, boundary conditions. These are modes from these transducers. If they're degenerate modes that drive, let's say, the top boundary, like shown here, you know, they say orthogonal modes, then you get the following vorticity field right here, or this, the arrow is actually the forces, you know, and this is the angle. So you get torques into the whole cavity. Now that's, if you control that, for example, if you know the phase offset, In our experiments right now, we don't control that. But we also don't constrain, of course, that degree of freedom at all. We constrain the lateral, we constrain vertical motion, we don't constrain rotation. So any asymmetry, for example, in the scattering that scatters off into the levitation plane can set off a rotation. Or of course, you can excite various modes of excitation, and where one of them then couples eventually into a rotational mode, right? So turns out, though, that the movies I showed you, they're taken with high-speed cameras, right? So they're actually rather short in time. So if you look at this coalescence here, we're talking about what, a few dozen of milliseconds. If you look at this whole breaking apart, that happens over a few hundred milliseconds. And here, what I'm showing you, what Melody measured, are 3 instances in these 3 different colors of rafts moving around, rotating over time. And now we're talking about a minute. Right, horizontal axis is a minute, and this is the rotation velocity. So, for example, dark purple, the thing just basically oscillated back and forth ever so slightly, just a little bit. It just wiggled, right? And sometimes it stopped, sometimes it changed direction. And then you look at the blue trace, there are long stretches, for example, here where it just increases rotation velocity almost linearly. So that's your constant torque right there. You can find all sorts of spots that way where you can zoom in and use that to drive the experiments I'll show you next, okay? So here again, this is the experiment, short time scale. You see this thing move out. So now what we want to do is look at how does this thing deform, right? So we took gravity out. So now this is just spinning up. So there is one parameter is the long axis over the, let's say, the initial diameter of this pancake. And you want to do that as a function of rotational energy. Now, spinning objects like that have been looked at before. I'll tell you in a second, but let's just look at the experiment here. So you should read this in the following way. I'm plotting this parameter, how much things deformed on a vertical scale. I'm plotting the basically rotation frequency squared on the horizontal scale. So that's the energy here. And you should look at this, like my cursor goes. You start out here, you increase the speed because it gets torqued up. It goes faster, 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 faster. Eventually, it actually slows down, but it hasn't changed shape much. And then it changes shape much. There's a little kink here. And by the way, as we do that, we can go in there and see all the particles like you guys do with colloids, right? And we could look at defects and all sorts of wonderful things. We can go up further. We can identify how these kinks then have to do with eventually stuff flying off, right? At this stage, this thing hasn't totally split apart yet, but certain pieces might be coming off, all right? And then you see this was for a particular size of raft, and the scale here, the color scale on the right, tells you this what about maybe 150 particles or so totally in there. And you do the same thing for different sizes. These are just representative traces. Eventually down here, the black one is maybe for, let's say, 50 or so particles. It's a tiny raft. You see in all of these cases, these rafts spin up without changing shape much. And at some point they start changing shape, right? And what's not shown here, because we only go to 1.8, we're not showing where they break apart. That's not part of this. It's just how do they deform, right? Now, this whole idea of watching something spin up and then deform is interesting in various contexts, right? In very different contexts too. And here's one. So that's liquid drops that rotate. And that is something that goes back, way back. I mean, goes back to Chandrasekhar and others, even way before that plateau, in fact, in the 1800s. And one idea was that if these are charge droplets, to think of this as a model for nuclear fission, in fact, right? So the second thing was, of course, well, you have surface tension that holds things together in these liquid droplets. That's maybe like self-gravity. So Chandrasekhar and others, they looked at these things also because they thought of objects in outer space that spin, and form different shapes that are non-spherical. And so the idea is that you compare rotational with surface energies. Well, and so if that ratio hits some critical value, then you go away from a sphere, right? And here's from this paper from Brown and Scriven from the 80s, how that is with velocity in the horizontal axis. And this is exactly this parameter, R max over R. And you see that at some point you spin it up, not much happens. It gets a little bit aspherical. And then there's an instability from a sphere, actually, in this case, into something two-lobed. And I show you a picture up here from their paper, what that means, right? It goes eventually into two-lobed systems. And you can even have apparently three-lobed and four-lobed shapes. But see, there's always a maximum. At the maximum, this thing gets unstable, and then it deforms. These things still rotate, right? And so we can look then at these points, and it turns out that these critical moments here, of course, depend on the rotation speed and the surface tension. So if you look at where an instability happens, you get an idea about the surface tension. So this is a wonderful way of getting surface tension out. But before I get there, what about this point here with self-gravity? Turns out that very recently, in fact, right now, people are looking at particular objects, and those are asteroids, and they are rubble piles. So these are granular systems that are held together by nothing else but presumably self-gravity. So now they are hundreds of meters, maybe kilometers apart. So you see these asteroids down here. These are recent simulations, actually, or maybe, okay, 2008, not so recent, from people like Kevin Walsh in Boulder, where they approximate these shapes now in 3D by granular systems that spun up, and then wherever it's white, particles roll off or get kicked out, and this thing gets more and more oblate, right? And so that resembles a little bit what we have in the equatorial plane. In fact, if you look at some other calculations here by Hirabayashi, depending on what they think is inside of these asteroids, for us, it's probably the same stuff everywhere, so they're homogeneous. So you have two possibilities. Either they just crack apart, or they just get more and more oblate and eventually just spit stuff off, right? So we, in fact, and I don't have time to show you that, we see both of this. This is the little guys, this is the big ones, except for us in 2 dimensions. So how do we do that? Well, you look at now our plots here, Melody's plots, and you just look, let's say, at the cusp, all right? And then you relate the cusp location to the surface energy, which in turn depends on surface tension, right? And you get something out where it says surface tension apparently changed here depending on what the number of particles was inside, or did it? I mean, if there was a liquid, the surface tension shouldn't have changed, right? That should have been a number. For water, 70 millijoules per square meter. Well, look what we find. We find that that effective surface tension interfacial energy depends very much on how particles are in there. In fact, the cool thing is this is a little bit like gravity, right? It does change the bigger the thing gets. And this is more or less linear, in fact. And the best thing here is also we can change the slope, right? How steep that is, by changing how much energy we pump into the whole cavity. So the slope is gamma over n here, and change that by how much piezo voltage we put on there. So you can, over some range at least, we can change that. The interesting thing here is, though, that this is absolutely not expected from what you would imagine if you think of point scatterers, right? So if I just use the Silver and Bruce idea and I measure, what would it take to pull a particle off a raft, a 2-dimensional raft right here, there's, the energy it takes, normalized in some way. Don't worry about the prefactors, just worry about the dependence on how many guys are in the raft, right? You see that we see this very steep dependence here, and Silver Bruce would predict this very shallow dependence there based on just simple mean field scattering of point particles. So there's really something now where theory and experiments don't match anymore, and we need an update of the available theory right now. So I want to sum up for you. I hope I have convinced you that acoustic levitation of granular little particles can really be a beautiful new platform for granular physics. So we can tune the strength of these attractive forces due to scattering. We have an access now into this regime of underdamped dynamics. And by detuning a little bit, we have active fluctuations. I showed you 4 examples here: collisional charge transfer, assembly of clusters, shape dependence interactions, spinning rafts, right? Of what one could possibly do with it. Now, there are really some questions out there. What do you do if you want to scatter of larger, not point particles, and moving objects, right? What about non-conservative forces and torques? I mean, how exactly can you control that? I think what you guys do at NYU really sets the path for that, but but we collectively, I mean, we need to do something about it. We're not there to understand what we see quantitatively, certainly. And then there's some beautiful extensions possible. For example, you immediately will know that we have access to all the particles. We could go in there and look at defects and all that. We've done that. I don't have time to tell you about that. So how does the soft solid really break apart exactly? So these colors are the 570 defects. What about bending instabilities? What about different particle shapes? I mean, you could float all sorts of things in there if you maybe 3D print it, right? What about swarms of particles? I'll just take 2 minutes and just show you some more really exciting stuff fresh off the cooker here. So look at this thing. Isn't that cool? So now you make this thing so large, it's like a pizza, right? And there's a fluttering instability, and then it breaks apart, right? So there's beautiful dynamics in there that we can get at with this. And certainly if we had a little better camera, even more detailed, right? That's one thing to explore. Here's another thing. So look at this, Tali, another graduate student. You now have shapes that are not spherical and make them collide. And we're tracing them on the right? Look at that. So they bounce off, but they bounce off in a very interesting pattern, which is essentially perpendicular to the way they came in. Rather interesting, rather tantalizing. Why do they do that, right? So we're working on that right now together with Vincenzo. And then, of course, these particles I showed you were small with respect to the wavelength, but they were large with respect to one more scale in here. And that's the viscous skin depth, the boundary layer, acoustic boundary. That's how the air couples to the particles. See, that thing depends on the viscosity, kinetic viscosity, density of air, and on the drive frequency. We had 40 kilohertz or so. Ours are about 10 microns. And I showed you Silva and Bruce, that's the dark line here. Melody just recalculated it. Now you put LBM to task, and you see right when these things come really close, that's actually modified. Scattering theory doesn't catch it. And new things happen. And now you do that as a function of particle size. So you see scattering theory is pretty good for the big particles. It's the dark line here. LBM is the data. It hugs the scattering expansion. But as the particles get to approach the viscous skin depth, look what happens up here. We're factor 3 away from the skin depth. You almost get repulsive interactions. Look at that, right? And that is so cool because now you can put these particles in. So what did I say? Skin depth is 10 micron. Let's put in 20, 30 micron particles. And now you see this. Huh? Who ordered that? There's a vestige still of the aggregation in these planes, right, on these rafts, right, roughly in the nodal plane, but you see these beautiful swarms of particles around. Anyway, I just want to give you an idea of what else is coming. This is the current group. Here's Melody, Brian, Tali, new graduate student Brady, and Annie, the undergraduate, and Anton, who is now at Bath, and Vincenzo. And I told you already about this, so let me just stop and thank you for your attention.
All right. Thank you so much, Heinrich. That was what a lot of fantastic stuff. So this talk is open for questions, and I encourage people to come in off the floor to ask them. And I'm going to kick it off. So you touched on this. You touched on the idea of looking at asymmetric particles. So essentially to use geometric asymmetry to create, I would guess, active like swimmers, right? Swimmers through air. Is that the plan?
So we'd love to be able to control things now. Can we exactly make swimmers? So you saw these swarms, right? So that is like it. You can imagine that we can 3D print or otherwise fabricate particles to scatter in particular directions preferentially, put them together with appropriate particles and make compounds basically by design. Yes, those are ideas, but at this stage, they're not there yet.
can you measure the temperature of your swarm? Do you have enough information to do that?
You mean essentially the kinetic, the RMS fluctuations of a swarm?
For example, or if you just have a good snapshot, maybe configurational temperature.
I think we can. We need, we need to actually do that. That can all be done. And I think we can learn a lot from what you guys did in the colloid business and just transfer this over. At this stage, it is essentially taking data with probably multiple views, and that can be done with mirrors or multiple cameras and synchronize them. Yeah.
Heinrich, are there situations in which gravity plays an important role? What might happen if you had particles with different densities?
Yeah, so that's exactly right. And then they would float at different levels. So I mean, we with these transducers, you can also levitate metal particles, right? But then they sink more, right? Yeah.
But then I just wonder how if you had different types, how that affects their self-organization, how they scatter off of each other. Have you looked at that?
Yeah. So yeah, to some degree. I should preface all of this. So what you saw was of course a broad brush overview. We have more, but it is true that for us this is a very exciting platform we have not explored to the nth degree, right? So in terms of scattering, the density of the particles does not matter much as long as you are significantly denser than the surrounding medium. So by the time you're solid, the differences are in the fourth, fifth digit, and we don't know how to pick that up. I mean, that is such a subtle thing. Mm-hmm. In terms of other things, I mean, if these are magnetic particles, so you can imagine coming in with magnetic fields or electric, I showed you dielectric particles. So now you got an open platform with open sides to bring in anything from cameras to fields to whatnot. And so, yeah, there are plenty of possibilities to extend that.
So I see Eric Brown from Yale has raised his hand.
Hey, Heinrich.
Eric, all right.
So you showed this cool connection between the wettability series and the triboelectric series, and that went by kind of fast. And I want to make sure I understand it because it sounded really cool. So I think if I understood correctly, so I think of wettability as a liquid will wet a surface that is more conductive or at least more polarizable than the liquid. I think that's the traditional picture. And that seems to be comparable to the, I guess, an idea in the triboelectric series that ability to polarize is also going to relate to the ability for an electron to move to another material in contact. Is that the idea there?
Yeah. So that, I mean, yes, but more generally, the triboelectric series worries about different materials and probably because of the electronic structure and things like that. I think the point I really would like to make is that in the end, what we find for is certainly the particles we looked at. So anything from glass to ceramics, typical particles you might experience both on Earth and in outer space there. I mean, these are presumably water crystals, right? That are crystallized that are floating around a star. That you have small amounts of surface water on this. And as you know, it doesn't take long for any surface, unless it's an ultra-high vacuum, to get a molecular layer of water on it, right? At 1 second at 10⁻⁶ torr. So I wouldn't be surprised if that happens essentially all the time. And that's basically what we're saying.
Okay, so you're suggesting that I guess the more hydrophilic materials are going to get that water layer more easily.
Exactly. And that's precisely what we actually see. So if we go with hydrophilic or hydrophobic, we see exactly that trend. Yeah.
Very good. Thank you.
Heinrich, can I ask if you
actually, Paul, just 1 second. Mike has patiently had his hand up.
fine.
Sorry.
Should I put my hand up?
Please do. Yeah, that'd be great. Mike Ward, did you?
Yeah, follow the rules, Paul. Heinrich, great talk. What if these particles had sticky, surfaces? when they collide? Would you find kinetic traps or unusual shapes that were modified compared to what you're seeing in the field?
I bet yes. And look, obviously, as these things come together, there's just the acoustic force driving it together, but then there are other forces that potentially can play a role, right? Eventually, they stick to all sorts of forces, including whatever beautiful chemistry one would put on the surfaces. And that's something we'd love to explore more. I should say one thing I forgot, and this is really important. I started with this charging business, right? And then I kind of dropped it. And you might say, well, what about charging? I mean, aren't these particles charged and don't you have to worry about that? And we worried very, very much about it initially. And it turns out that these acoustic secondary forces from the scattering between particles in our setup, though, are typically overwhelming the electrostatic forces unless you really charge particles up, right? So, I mean, and if you work on that, let's say shake them around a little bit beforehand, yes, that matters, right? But normally, if we use conducting surfaces so that particles, when they land, they can be grounded and all that. So then charges doesn't matter. But, what about functionalizing the surfaces so that when things come together, you can make them stick? You shine light on it. I mean, all of these things are kind of in the toolbox now and ready to go. Yeah. You could temperature on there. I mean, it can heat.
Sure. Yeah. Well, sure, you can use temperature to sort of as another handle to regulate the assembly, right? And very cool. Yeah.
I guess Todd Wilson is next on the list.
Yeah, what are the largest useful nodal plane regions you've achieved to do your experiments upon?
What are the nodal plane regions, you mean?
Yeah, the area of the region. What's
how
largest?
wide can you make that?
Yeah.
Oh, that's a great question. And I would think that you can make it very wide, I mean, literally as wide as you can make transducers uniformly vibrate and not flex, let's say, or otherwise deform the local input. We have not tried to make things particularly large, right? So everything I showed you with these videos, these are tiny particles. We're focusing on a few millimeters central region of a transducer, which is circular in our case, and typically 5 centimeters across or something like that. I showed initially some pictures from Drinkwater and other places where they make these arrays of tiny rangefinder transducers, and they can be table size, right? So the big one was 996 transducers. So that is massive. And so presumably you could make it even bigger.
Yeah, and I noticed the densest particle I saw in the presentation was maybe a glass sphere, but then you mentioned grains that were metallic. And I wonder what kind of sound pressure levels you require for levitation of those objects.
Okay, so give you an idea of the order of 160 decibels. So it's probably what a jet engine next to your ear would sound like. And we can levitate with slightly modified transducers. If we go all the way to the top there, a ball bearing, a few millimeter size ball bearing is no problem, right? We have even levitated, iron filings or similar things, meteor dust, stuff that's seriously heavier than glass.
Yeah, good. Thank you. Loved your presentation. It's fascinating.
All right. Actually, it looks like Paul Sanchez had his hand up, but maybe his hand is down now.
No, I'm here.
Okay. Your hand went down, but your voice came up, which is good. Please ask your question.
Yeah. Sorry, I think that there was a problem in the connection. Thanks for the talk. It was very good, very interesting. My name is Paul Sanchez, University of Colorado Boulder. I was actually working with Toshiga Hirabayashi. Yes, yeah, I am the P. Sanchez in some of those papers.
Great.
I was wondering, well, in asteroids, you have usually very wide distribution of particle sizes, from millimeters, well, actually from microns to tens of meters. And you don't have the viscous fluid around them. So I was wondering how applicable your experiments really are to asteroid formation and asteroid evolution. Or what would you need to do to make them really applicable to them?
Yeah, no, look, I mean, I'm not sure about that. I'm tickled by possible connection, but look, we don't care about the surrounding fluid here right now. We are saying our systems are held together by some interfacial energies. They come from the secondary scattering, we think, right? And they act like a surface tension of a particular kind, which actually increases with the size of the object, right? And now we spin our object to the point that it eventually goes beyond being stable and breaks apart. And if you look at what's up here right now, this slide, you see these are semi-crystalline little packings, you know, because we use same size particles. And that's why they form these beautiful arrays. But white here is mostly 6 and particles surrounded by 6 neighbors. And then there are the ones in green with 7 and purple with 5. Now, if I had used the size distribution, then I could have easily, I'm very sure, we could have easily made this not a crystalline solid or semi-crystalline, but really a more amorphous solid, right? And now we don't get to 10 meters here, but I think the deformation types, right, and how it deforms might be able to scale down. At least that's the hope. Look, yours are 3 dimensions, these are 2-dimensional. This can only approximate what possibly happens in the equatorial plane. Yeah.
Okay. Any chance you can actually get a 3-dimensional shape, or are you constrained to having this quasi 2D surface?
Well, right now we're pretty much constrained. So with the setup I showed you and I told you about, you know, get a lot of pressure from above, a lot of pressure from below. The thing wants to be flat like a pancake. It's a good question whether one can build up more 3-dimensional objects. So we'll have to see.
All right, thank you.
Right now we can.
Thank you.
Paul, you've been so patient.
Okay, well, one of the questions you sort of already answered. I wondered whether if you charge them, you could get something like a dusty plasma.
Yeah.
But I guess you have to be much smaller, is what you're saying, that the forces, the attractive forces will overcome the electrostatics.
Yeah, so look, I think that's a direction we as a group would really love to go further into. There's also Justin Burton at Emory, right, who does both essentially now that the dusty plasmas already. It turns out the Gorkov acoustic potential, the force from that, right, that I showed you over only the close approach, right, where it's more or less flat and then dives down, so you really attract things on essentially touching. If you went out to a wavelength, and a wavelength on that plot would have been, you know, next door.
I see.
There are slight fluctuations, there are slight variations at a wavelength. So in principle, one could stabilize particles a wavelength apart, even in the sound potential. And that's something Silva and Bruce also calculated. They found that, right?
But these are just sort of held in place by the acoustic field.
Yeah, that would be all acoustic field. And I always was hoping and thinking, and we just haven't gotten there yet. We charge the heck out of these particles and maybe prevent them from coming together. Let's say make them all positive. And then you got that as a repulsive force, but then you got the sound field or the potential to bring them in, right? And we get we got a dusty plasma essentially, yeah.
The other thing I didn't quite understand is the droplets. That is, you said that they remain spherical, even if you don't, suppose you don't spin them or anything. You said that they remain spherical until an instability, but doesn't the acoustic field squash them down? Doesn't it make them non-spherical immediately?
You mean the liquid droplets?
Yes, the liquid droplets.
Yeah. Okay. So sorry, the slide I showed you, and I don't want to race right back, but you want me to bring it back up?
No. Just
that slide was theory by Chandrasekhar and also later by Brown and Scriven.
It must be right if it's by Chandrasekhar.
Well, no, I mean, it was without gravity, just a spherical drop in outer space, right? And no sound field. They didn't think of sound fields. But actually Scriven thought, and he wrote it in there at the end in this paper, that the way to test that would be on the space station or whatever, somewhere out there with acoustics. He knew that's how you get to there for liquid droplets. We are just taking these ideas and saying, okay, liquid droplets will have this maximum rotation rate before deformation can pull out the surface tension. Right. And we use that approach to pull out the effective surface tension for us.
But if you just use a liquid droplet and you don't spin it and you just put it in your acoustic field, does it go to the middle and make a pancake?
Yes, it will do that. It will also make a toroid. We can squeeze it so hard, it will spit stuff out to the side. It will oscillate, it will pump. I mean, we were pumping energy in there. We can pump it so hard, it'll spray it apart with satellite drops.
If you don't pump it, if you just have your acoustic field, does it just make a pancake?
Yeah.
Okay, fine.
But I don't know how, look, so that we didn't do systematically. I don't know how far I can push it. And yeah.
Okay. I just want
to
know.
It'll do this.
Very cool, Heinrich. Very cool.
Thanks, guys.
All right. If there are, I see hands are up. I don't know if those are residual hands up or are they new hands up. Yassine Amarashin is a new hand up. So
yes. Hello.
Hi.
Yes, Yassine Amarashin from Bordeaux. Very nice and interesting talk. Amazing. I have just a few comments, maybe some questions, essentially on the droplets, exactly as Paul Chaikin. Did you manage to measure the fluctuation of the shape? Is there any modal signature of the surface tension?
Yes, you could. You mean for liquid drops?
Exactly.
If we did it. So we didn't measure liquid drops. So this is, I should tell you that. So everything we did in my lab, we just focused on the granular situation. Other people have used this for liquids, but we didn't focus on that.
No, I mean for the granular drops. So you're spinning particle drops, they oscillate. They have a kind of oscillations. If you do a Fourier transform of the shape, do you have any resonance?
So that's something we have not explored. It's a good point. No, we have not done that.
Even the damping.
What do you mean? You mean damping in this direction? Or?
No, in the shape. Imagine you have a shape.
No,
so
but,
if you have.
I see what you mean. No, we have not done that. I think it might be hard for us in the current setup to pull that out, but that's something we haven't done. Yeah, I know what you mean, but that's not what we have done.
Okay, because it will be another way to estimate a kind of effective surface tension in your system.
Absolutely.
Directly.
Absolutely, yeah. I mean, the droplets are still so small. They're in what you maybe call a mesoscopic regime. Where
exactly.
You see facets. So you see the particle nature. I mean, you can count the particles still, right? And so this soft solid, it doesn't deform as like a liquid yet. I mean, as you guys all know, it has to have defects first and planes of deformation where things slide around and all that. So it might be interesting to go to an amorphous system. Yeah,
I see. Another question concerning the tuning of the acoustic cavity. So I guess you managed to measure very precisely the wavelengths, or knowing the temperature, the humidity, and the frequency of your transducer. But how actually do you tune the cavity? Because in optics is quite it's a job in itself, but for acoustic, how do you tune that?
So this is something I will give you a very quick answer, and if you really want to know all the nasty details, then you need to contact, let's say, Melody Lim, my graduate student, or one of the others there in the group. So basically, literally, you can tune it by the following. You say, when there's resonance, that's when this thing will float, right?
Yes.
And so you put it in there, and you basically change the gap height. And we can't change the frequency because, look, the transducer has a resonance frequency. The transducer is a stack of piezos. I didn't really talk about that, with a horn underneath. And the horn is finite element simulated to hopefully, as good as we can, pump out vertical vibrations if it's excited on the top, right? Okay. And so that it does at its frequencies. The only thing we can vary is the gap size there. to get into resonance. And for that, you use a micrometer and just move the reflecting boundary back and forth until the little guy
Okay.
floats, right?
But it still floats on what it's not, you have a kind of tolerance against the tuning of the cavity, even if it's out of tune. If detuned, it still trapped the particle.
Yes, it does, very much so.
Okay.
That's rather good. Yeah. But our
Yes.
cavities don't have a high Q. Don't forget, you know.
Okay,
Q
I
is
see.
only maybe 100 or so. We're not talking a million.
Okay, I see. Thank you again for your very nice talk. This
Thanks
was
for
amazing.
tuning in from all the way Bordeaux.
Thank you very much.
All right.
I had one more question.
Dig in, Paul, please do.
Okay, so just to get an idea of how big the acoustic field is, what the pressure is, how big a bug can you levitate before you kill it?
These are two questions in one, and we have, unfortunately, we have not addressed either one.
Wait, I mean, can you levitate living things without destroying them?
Yeah.
But probably not a frog, right?
Nope. For that you get an Ig Nobel Prize, and we didn't shoot for that.
Okay.
That was magnetically done, as you know, in Florida.
Right.
But I in that review, for example, Andrade that I showed, you know, he has an image in there, a little bug, you know, a fly, or actually it was two of them. I would be rather interested in what several would do, but we haven't tried that yet.
Okay.
I think it would be interesting. Yep.
Okay.
Maybe just a comment from me. Paul, this is Paul again from Boulder. I have a simulation that looks exactly like the one at the bottom right that you have in there. It's in 2D too.
Oh, you mean for the 2D asteroid?
Yeah. Looks exactly like
that. Please contact me somehow. Shoot me an email. Call me up. Lovely to talk to you. Fabulous.
And I see Todd's hand just went back up again.
Yeah, so you're talking about the piezoelectric stack in the sonotrode connection, the horn. It just got me thinking about what kind of electrical power have you required in driving this assembly, this transducer?
Okay, so I can't tell you that exactly right now. I can give you some ideas about the other parameters, not power, but so voltages, a couple hundred volts. It means a stack typically of maybe up to 4 of these disc-like piezo elements. And we use a bipolar amplifier. I mean, the trick is to go 40 kilohertz, couple hundred volts plus minus like this, right? So that's how we do it. And those are, that's the special part, the amplifier. But the current is low, right? So that helps, right?
So it's like a capacitive load that's being driven.
Yeah, essentially.
High impedance.
Yeah, it's high impedance, low current. So in some sense, the power isn't big at all, right? It's just a high voltage.
Yeah.
Or high, semi-high, a couple hundred volts.
So then I'm thinking about how much excursion peak to peak does the face of the transducer need to move through to, let's say, get 160 decibels at 40 kilohertz. Any ideas there?
Yeah, so I should have these numbers at my fingertips. I don't, so I would have to go back and get them for you. No, that's a good point. Yeah, absolutely. Yep. But it is a lot of sound pressure. That's true. Yeah.
All right. Well, that sort of really ends us on an interdisciplinary note. Granular matter, gas physics, electrical engineering, the whole 9 yards.
Yeah, don't forget Astro.
No, don't forget Astro. No, so we've covered a lot of length scales here and time scales. So I propose that that we thank Heinrich one more time for just an outstanding presentation. And I will turn off the recording. You don't have to leave. In fact, I encourage you to hang out and chat just informally now that we're done with the formal part of the session. So thank you all very much again for coming, and I look forward to seeing you all again soon.